In addition to horizontal curves which go left or right, roads also have vertical curves which go up or down. Since they appear in the vertical plane, they are called vertical curves. Learn more about them here in engineering surveys. With the different terrain in the field, not only shall roads and highways adjust horizontally, but even vertically. A curve which concaves upwards is called a crest curve. Such a curve is designed using parabola and its elements, with the reasons that a parabolic curve is easy to set out on the field, and it also provides a smooth transition between gradients. A curve concaving downwards is known as sag curve, where a cubic parabola is the most preferred for the design as it closely approximates transition. As introduced earlier, the two general types of vertical curves are the crest and the sag curves. Crest curves are also known as summit curves or over verticals. They appear when two tangents meet, whereby they produce a curve concaving upwards. The different ways to find crest curves are through computation of the grades are the following. The most common is to start with a positive grade P for tangent 1, then followed with a negative grade Q for tangent 2. Note that this combination will create an upward concavity of the curve. Another circumstance is by having two positive grades. However, the first grade P is steeper than the second grade Q. In this case, although both P and Q are positive, the curve still concaves upwards. The third case uses two negative grades. In the third case, the second grade Q is steeper than the first grade P. Such combination will create a curve concaving upwards. The second type of curve is called sag curve, which is also called under verticals or valley curve. In contrast with the first type, sag curves concave downwards. Three ways to designate a sag curve are as follows. First, using a combination of plus and negative grades, whereby the first curve P is a negative grade followed by a positive grade Q. Thereby, the formed curve sags or concaves downwards. The second case uses both negative grades, where the first grade P is steeper than the second grade Q. And the third case uses both positive grades, where the second grade Q is steeper than the first grade P. All combinations with their special conditions create curves concaving downwards, thus they made sag curves. Symmetrical parabolic curves does not necessarily mean the curve is symmetrical at L all over 2. It simply means that the curve is made up of a single vertical parabolic curve. Using two or more parabolic curves placed adjacent to each other is called unsymmetrical parabolic curve. Let's learn the elements of a vertical curve. PVC, or the point of vertical curve, is the place where the curve begins. PVI, or the point of vertical intersection, shows the spot where the grade tangents intersect. PVT, on the other hand, shows the place where the curve ends, and it is called point of vertical tangency. G1 is the grade tangent at PVC. G2 is the grade tangent which connect PVT. Both of these grades are measured in percent of slope. At PVI, the algebraic difference of the grades is known as A. L is the length of the curve, which is actually the horizontal length measured from PVC to PVT. Most often, L is distributed between L1 and L2, which are measured from PVI moving outwards to PVC or PVT. What about the basic formulas to keep in mind with vertical curves? First are the vertical distances of the stations PVC and PVT from PVI. They are designated as A and B. Since grade is the slope, with the formula rise upon run, we can derive A and B from the triangles. So, G1 is rise of A upon run of L sub 1, and rearranging parameters we get A is equal to G1 times L1. But we know that L1 is half of the horizontal length of the curve L. So A is half of G1 times L, and so is B taken as half of G2 times L. Next is the horizontal location of the highest or lowest point of the curve. To derive this formula, use the grade diagram, and by proportionality of similar triangles, we can draw the relationship S1 is to G1, which is equal to S2 is to G2, and is also equal to L all over the summation of G1 plus G2. Thus, S1 can be computed as G1 times L all upon the summation of the grades G1 plus G2. This is similar with S2, which is taken as G2 times L all over G1 plus G2. The vertical distance of PVC to the summit is H1. PVT to the summit is H2. These two parameters can be derived using the area of the grade diagram. Since we have a triangle, we can take the area as half of the base multiplied by the height. So H1 is equal to half of S1 multiplied by G1, and H2 is derived the same way. The maximum offset H is equal to 1/8 the product of the algebraic difference between the two rates of grade and the length of the curve. The last formula is the vertical offsets from the tangent to the curve, which are proportional to the squares of the distances from the point of tangency.